Have you ever stopped to think about how a machine actually learns to do something that's super easy for us, like, just recognizing a flower? It's definitely not magic. It's this really fascinating process of trial and error. So today, we're going to follow a little digital brain as it goes from its very first clumsy guess all the way to perfect accuracy. And in the process, we're going to uncover a huge lesson about what it really means for an AI to learn something.
So here's the core challenge, the big question. We're not giving the computer a photo. All it gets is 4 numbers, just 4 simple measurements of a flower. Is it possible for it to learn how to tell 3 different species apart based only on that tiny bit of data? Well, let's find out.
Okay, so to pull this off, we're going to use a real classic from the machine learning world, the iris dataset. Think of it as the perfect, clean little sandbox for teaching a machine a new skill. It's got all this data on 3 different species, Setosa, versicolor, and virginica. And our mission, should we choose to accept it, is to train a model that can tell them apart.
Now this, right here, is what the computer actually sees. Not beautiful pictures of flowers. Nope, it just sees rows and rows of numbers. Each row is one flower, described by its measurements, and, of course, the correct species label. This raw data is literally the only thing it has to learn from.
These are our inputs, or what the data scientists out there call features. For every single flower, the machine gets these 4 specific measurements. Its job is to somehow find the hidden patterns buried inside these numbers. And these are the possible answers, our targets. The entire job of the machine is to take those 4 feature measurements and correctly slap one of these 3 species names onto the flower. Sounds simple enough, but how in the world do we actually get it to do that? We do it by building it a brain, a small digital one. The tool for this job is called a neural network. It's a model that's kind of inspired by the human brain, and it's designed to learn really complex patterns by pushing data through a bunch of different layers. Now, the specific job we're giving our network has a technical name, multiclass classification. I know, it's a fancy term, but it's for a really simple idea. For any given input, our flower's measurements, the model has to pick the right label from a list of several possible classes, or in our case, the 3 species. So here's a peek under the hood of our network. The 4 measurements go into the input layer. Then they flow through 3 hidden layers. This is where the real thinking and pattern matching happens. And finally, the output layer makes its best guess, producing a value for each of the 3 flower types. But here's the cool part. The output layer doesn't just blurt out a single answer. It uses this clever mathematical trick called a softmax function. You can think of it like a funnel that turns all the raw calculations into clear probabilities. So the model can say something like, okay, I'm 95% sure this is a Setosa, which tells us how confident it is. All right, the model is built. We set it loose and train it for 1,000 cycles, or epochs. We're basically letting it look at the data over and over and over again to learn the patterns. And at first, the results look amazing. But you knew there was a but coming, right? There's a twist. Get this. On the data it trained with, our model hits nearly 98% accuracy. That's fantastic. It's learned to classify the flowers it studied almost perfectly. You think we're done, right? Mission accomplished, high fives all around. Well, not so fast. Here comes the reality check. The moment we show the model new flower data from a test set it has never seen before, the accuracy just tanks. It plummets all the way down to about 83%. That is a huge drop. What on earth just happened? This really dramatic drop in performance, it's not a fluke. It points to a super common classic problem in machine learning. It's time to name the villain in our story. And that villain has a name. Overfitting. This is such a critical idea. It's just like a student who memorizes the exact answers for a practice test, but doesn't actually learn the subject material. The second they get the real exam with slightly different questions, they completely bomb it. Our model didn't learn to see flowers. It just memorized the training data. This chart right here basically tells the whole story. It shows the model's error rate, or loss, during training. The blue line, the training loss, goes down nice and smoothly. But look at that orange line, which represents the test data. It's all over the place, fluctuating wildly. That instability is the classic visual signature of a model that is totally overfitting. But here is the good news. We do not have to throw our model in the trash and start all over again. We can totally fix this, and all it takes is a couple of smart, simple adjustments to how we train it. So Here are our two little fixes. First, we just stop the training way earlier at 250 cycles instead of 1,000. This basically gives the model less time to just memorize everything. And second, we swap out our optimizer. That's the algorithm guiding the learning to a much more advanced one called Atom. And this quote from the source material really explains why that second change is such a game changer. The original optimizer, SGD, is fine. It's a good place to start. But Atom is way more sophisticated. It automatically adjusts how the model learns on the fly, helping it find the best answer faster and a lot more reliably. And now, just look at this graph. This is the learning curve after our fixes. See how the blue and orange lines now track each other so smoothly and so closely? This, my friends, is what a healthy, stable learning process looks like. The model isn't just memorizing anymore, it's actually generalizing. And the result? A perfect score. 100% accuracy on test data it had never, ever seen before. By training smarter, not just longer, our little digital brain has now truly mastered how to identify these iris flowers. This quote really just nails the whole point of our journey, doesn't it? Building a successful AI model isn't about finding some single magic algorithm. It's an iterative process. It's about choosing the right settings, those hyperparameters, and carefully guiding the model to a real, general understanding of the world. So, how much of AI is magic versus just careful tuning? Well, what we just walked through, building something, finding a flaw, diagnosing it, and then applying a fix, that really is the heart of the matter. It shows that progress in AI is so often less about a single stroke of genius and much more about this careful, thoughtful, and iterative process of just making it a little bit better one step at a time.